Math is hard, so I'm making you all suffer with me. Hello, Future Davis here. Yes, I got a haircut. Yes, my room is different. I'll talk about all that in a future video, but I just wanted to say, I know I've been doing this a lot lately without meaning to, but at least for now, I am definitely not going to continue this series. I just finished editing this video out of sheer determination, and it was hands down one of the most mind-numbing things I have ever done in my life. This is the longest video with the most amount of editing I have ever had anything to do with, which, like, in my defense, I'm trying to squeeze, like, 5 multi-hour lectures into this thing, and I did get it to under an hour, and while there are a couple of mistakes I just left in there because I couldn't be bothered to fix them, it did turn out great, so you should still watch it, but no way am I putting myself through that again anytime soon. I've continued to write my notes in the form of a script, which has helped me, and I might come back to this sometime in the future. Now, I'll still be making regular videos because normally I love editing and getting creative with stuff. It's just the number of hours of frustration with this is just in no way worth it. That being said, I did pass Calc 2. Alright, so this was filmed out of order. I don't know where I'm gonna put this in the sequence. It's actually Christmas Day, or no, it's Christmas Eve. Today, it's 9 p.m. Christmas Eve. I literally just got an email that my final grade was submitted for my math class, and I wanted to get my live reaction on camera because, once again, I don't need to stress enough that if I don't pass this class, I can't get an engineering degree. So, few grades, fall 2020. What do we got? Wait. That can't be right. No way. No freaking way. What? I'm speechless. I was hoping to just kind of scrape by with like a C, maybe a B tops. I honestly don't, like, statistically speaking, I do not know how that's possible. Well, Merry freaking Christmas. I'm gonna be an engineer. I mean, obviously I still have the next classes to pass, but this was the hard one. This is the one oh frick, I still have to take Chem 1A. And now I'm in Calc 3. But in the meantime, please enjoy the result of my blood, sweat, and tears. Good morning, boys and girls. It's your boy Davis, aka Fluffball, and welcome back to Calculus, taught by someone that doesn't get it either. Now, because I've been insanely busy, as always, and it's been a bit since the last one, this will be week 2 and 3 and 4. So without wasting any more time, let's get into it. Alright, so last time we covered a few different ways to do integrals, but what if we have something like integral of sine to the m of x times cosine to the n of x dx? We don't really have a way to do that yet, and there's a couple of different ways this can go, because those exponents can be anything. They can be, the main thing we're going to look for is they can both be even, they can both be odd, or you can have one of each. So if one of them is odd, for example, if we have sine cubed x times cosine squared x dx. So you can see the exponent for cosine is even, but the exponent for sine is odd. What we're going to do here is just strip off one of these to make them both even, because what sine cubed of x actually means is sine x times sine x times sine x. So what we're going to do is turn this into sine squared x cosine squared x times sine x dx. So you can still see we still have all three sine x's here. But now, what we can do is use this handy-dandy thing called the Pythagorean identity, which states that sine squared plus cosine squared equals 1. In other words, cosine squared x equals 1 minus sine squared x. So what we can do is say, I don't want that to be a sine squared, I want that to be 1 minus cosine squared. And then cosine squared x, and then times our sine x out here, dx. So that's looking like it might be a little bit nicer, and we can like distribute the cosine in the— No! Not yet! First, we make a substitution. So we're gonna say u equals cosine x, using the technique that we used last time, and then du equals negative sine x dx, which means du over negative sine x equals dx. So now our integral is looking like 1 minus u squared times u squared, and then the sine x that we stripped off earlier cancels out nicely with the result of our derivative to equal -1. So I'm just going to pull that negative out here and write du. So that's our new integral, and now we can distribute that and say that equals u squared minus u to the 4th du, and that's a lot easier. We just split it up, solve that, put the substitution back, plus c, and we're done. So that was a very simple case of this. There are a few more ways to work this out that I'm not gonna go over, but that's the basic idea. Now, if they're both odd, let's say we have sine to the 5th of, let's do 3x for fun, times cosine to the 3rd of 3x. Now, what you're gonna wanna do here, I've been told that you'd strip off whichever one gets you to a power of 2. Maybe it's like the lowest power of 2, because both 4 and 2 are both powers of 2. But with this one in particular, it's easiest if you do that to cosine, so that you're left with sine to the 5th 3x, cosine squared 3x, cosine x. So now we say this ain't no cosine squared, that's 1 minus sine squared. And you can see how this is looking a little bit similar here, so we're just gonna do our little substitution. I'm sorry, I messed this up earlier. This is supposed to be cosine 3x. Don't mind me, I'm just dumb. Okay, so then our du is 3 cosine 3x, following the chain rule. So now, if we substitute that in, we've got u to the 5th, 1 minus u squared, and then that will just give us a 1/3, which I can pull out here, du. Distribute that boy, and bada bing, bada bang, bada boom, plus c, and we're done. I think that's right. I'll double check these after I'm done and go back in post, but I'm pretty sure that's right. Now, if they're both even, we're gonna do something different entirely. So let's say we have integral of sine squared of 2x times cosine to the 4th of 2x dx. So for this, we're gonna use something called the half angle formula, which states that sine squared of x equals 1/2 times the quantity 1 minus cosine 2x, or cosine squared x equals 1/2 times the quantity 1 plus cosine 2x. Yeah, I just read that off my notes. So we got this integral. So we're gonna say sine squared 2x, what? Nah, that's a 1/2 1 minus cosine of 4x, multiplying that 2x by 2, times cosine to the 4th of 2x. Now, I don't know what my notes stopped here, but I'm gonna see if I can do this anyway, just by memory. Okay, update, I have no idea what I'm doing. I guess that's not really an update, but we're gonna maybe come back to this. So let's focus on something new. Trig sub, or if you're feeling rather verbose, trigonometric substitutions. So what if we've got integral of square root 1 plus x squared dx? Well, that's interesting. Now you might think, there's no trig in there, you freaking liar. I'm getting there. So let's take a look at this. Table? Nope. U sub? Nope. Parts? Parts? Not really. So what else is there? Let's think. I mean, looking at this, it kinda reminds me of the Pythagorean theorem, almost. With like the square root a squared plus b squared or something or other. Yo, I know! Let's slap a triangle on it! Or I guess more accurately, slap it onto a triangle, because this looks like the equation for a hypotenuse. So now what do you do? Well, we've got this, so that just let me fix this. We've got this, so that just means we know A and B. So if this is the hypotenuse, that just means we take the square root of this one, which square root of 1 is 1. That could be any number. Usually it's an even square so that they're nice to you, but that's what we do. Square root of 1 is 1. Square root of x squared is x. So we've got the legs of this triangle. So now we're gonna do something weird. The goal here is gonna try to be to get x in terms of the sine, tangent, or the secant of one of these angles. So let's just try calling this angle theta. And now we know tangent of theta is opposite over adjacent, so that would be 1 over x. Ew. Let's try the other one. If we call this one theta, and now tangent of theta is x over 1, which is just x. About as simple as it gets, so... Hey, guess what? We can substitute x just like we did last time with substitutions, except this time, instead of x squared here, we're gonna write this as tangent squared of theta. Now the question is, how do we get rid of our dx and make this whole thing in terms of theta? Well, that's easy. We know what x is in terms of theta, so just take the derivative. So if x equals tangent of theta, then dx equals secant squared theta, because that's the derivative, d theta. So now we just tack that onto the end of here to get secant squared theta, d theta, and that is our new integral. Well, that is just a trig integral. We already know how to do that. So we're gonna use the identity that 1 plus tangent squared is actually secant squared, so we can turn this whole thing into that. And then the square root and the square cancel each other out, so we're just left with integral of secant cubed theta d theta. And then from there we can do integration by parts. I'm gonna skip over that because it's long and boring, but we find that the integral is that whole mess. Now we're done integrating, but just like we did with substitutions, we gotta get this back in terms of x. So what do we do to get rid of that theta? Triangle's got us into this mess, triangle's gonna get us out. Let's slap a triangle on this boy. So basically, we just need to replace secant theta and tangent theta, because those are the only two terms we have here. So let's go back to the triangle that we had. We've already got tangent theta equals x, so that's easy. And then secant theta is the reciprocal of cosine, which is, let's see, cosine is adjacent over hypotenuse, so that means secant is hypotenuse over adjacent, which means secant theta is our hypotenuse, which was root 1 plus x squared, over adjacent, which is 1. And that can be simplified to just that. So now we sub those in, write down that whole mess, and we are done. Holy crap, I think we just used every single topic I've covered in this whole video series for one problem. Let's see, obviously we used derivatives and integrals. We used similar methods to substitution, basically substitution. Integration by parts, which I skipped over, but it was still technically used. We used trig integrals, all for one trig sub problem. Whew! So let's talk about what this actually works for, because this is not the only problem you're going to see. If we've got a squared plus b squared equals c squared. If you know nothing about math, you know the frickin' Pythagorean theorem. It's a meme at this point, I mean, come on. But like, we've got that, so that also means that doing some algebra, we can find that c squared minus b squared equals a squared. So that means we've got our formulae, root a squared plus b squared equals c, and root c squared minus b squared equals a. So to translate this into useful information, I'm gonna use the constant n instead of a or b to avoid confusion, but this means if something in your integral looks like root n squared plus x squared, or root x squared plus n squared, same thing because commutative property of addition, then that has to be the hypotenuse of the triangle that you use, meaning n and x are your sides interchangeably. So this is case 1, you've got this in here, that matches the equation root a squared plus b squared equals c, c being your hypotenuse. So your triangle is going to look something like that. And then you're going to want this angle as your theta, such that you have x equals tangent of theta equals x over n, or in other words, x equals n tan theta. Now, for case number 2, if you have something like n squared minus x squared, this is going to be different than x squared minus n squared. I'll talk about that in a sec. But with this one, the way you tell that this is going to be a leg, because it matches this equation, so you're going to be using c squared minus b squared equals a. And the reason you can't flip these is you can tell n has to be bigger than x, meaning n is your hypotenuse, because if it wasn't, we'd be subtracting a larger value from it, meaning we get the square root of a negative. Imagination! So if n is bigger than x, that means n is our hypotenuse, so that makes x one of the sides, whichever you want. I'll just put it here, and then the equation that we originally had as the other one. And then we want that to be x over n, which if we put theta here, would be adjacent over hypotenuse, that's cosine, which we don't really want, but if we put it here, then that's opposite over hypotenuse, which is sine, that's okay. So we say sine theta equals x over n, or x equals n sine theta. Now for case 3, as you might be able to guess, that'd be x squared minus n squared, and now you can tell x is bigger, meaning that's our hypotenuse. So this is going to be using the same equation as this, c squared minus b squared equals a, root of c squared minus, you know what I'm talking about. So we got our triangle, x is the hypotenuse now. I'm gonna put n here, this is our equation. And then if I put theta here, I think that's correct, because to get x over n, that's hypotenuse over adjacent, which is inverse of that's secant. Yeah, that's good. So secant theta, probably label that, is x over n, or x equals n secant theta. And those are the 3 cases that you've got. I don't think I mentioned, the reason we want sine, secant, and tangent is just because they're nicer to work with in integrals than their counterparts, which is cosine, cosecant, and cotangent. So just remember, if it has co in it, don't use it. Find another angle. It's really easy. Just switch whichever angle is theta. Also make sure it's x over n and not n over x, because that's going to be super easy to work with. Excuse me, I have a question. Why can't we just use one formula and cancel out the positive and negative and switch it around like constants and just pull out the negative like we do with everything else? What do the signs matter? We should just need one equation, right? Excellent question. The reason for that being a thing is because of this square and because of this square root. You can't just go messing with signs like that when you're subtracting squares, especially inside of a square root. The whole concept of what makes this work is by solving the Pythagorean theorem for each specific case. So while it might seem easier to try to do that and have less equations under your belt, it's not worth the extra work and everything's just gonna fall apart, and I didn't understand this until my 3rd time taking this course. But yeah, that's basically trig subs. You figure out which case you're dealing with, you draw your triangle, you sub back, and yeah, we're good. So, with that out of the way, let's go on to something completely new. That's right, we're moving on to week 3. So week 2, we focused on a bunch of trig stuff. Week 3, we're going to focus on something called partial fraction decomposition. Wow, that sounds scary, and I'll give you a hint, the integrals aren't a whole lot more friendly. I mean, just look at that guy. That's... Is this even possible? This looks messier than my mental state. Okay, so what partial fractions means is we're gonna split this fraction into parts. Parts? No, not like we did before. This is completely different. So the way you know this integral is even possible with partial fractions, you can only do a very limited number of these things. The top and bottom of your fraction both need to be polynomials. So that just means sums or differences with only x and integers as components. So no funny business with like square roots, fractional exponents, trig, anything like that. So polynomials. And you need the top part of your fraction to have a lower maximum exponent than the bottom, which is super confusing because there's not an easy way to remember that because it's lower on the top, even though lower is lower. It's confusing. Just remember that it's confusing because it's Calc 2 and nothing makes sense, and then you're good to go. By the way, that highest exponent in mathematical terms is called the degree of the polynomial. So on the top here, the numerator of the fraction, it would be 2 because that's the highest exponent, and on the bottom, in the denominator of the fraction, it would be 3. So that's the degree. You say this polynomial has a degree of 3. Now what you need to know that makes this whole thing work is the theorem that every polynomial can be factored into a product of linear and/or irreducible quadratic factors. What? Hold on. So linear factors look like that. Quadratic factors look like that. So for linear, a and b are just any constant, including 0. They could be 0, so x is a linear factor. All that means is, like, if you were to put it on a graph, x would just be going in a straight line. It's linear. Quadratic, since we've got that square in there, that means it's a quadratic or a parabola. And then what irreducible means here is you can't factor this quadratic into 2 linear factors, because that'd be pointless, just use the linear factors. So you need to factor it as far as possible, and if you can't reduce this quadratic, then that's one of your factors. So what this means is you can factor these polynomials into a series of some combination of these multiplied together with numbers in place of a, b, and c that you figure out, such that if you were to multiply them together and simplify it, you would get your original polynomial. So Once we know that the degree of the numerator is less than that of the denominator, we're just going to ignore the numerator until later on in the problem. So your first step is fully factor your denominator. That's the only thing that we're going to do this thing for with the factors. Now, there are a few different ways this can go. We're going to start with case 1, and that is distinct linear factors. And that means linear factors are the only thing that you've got in your equation, and none of them are repeating. Because if you have these that are repeating, then you'd say this linear factor squared or cubed or whatever, and that's a different case that we'll talk about later. But right now, this can be factored into distinct linear factors, so we're going to say this fraction would equal 4x squared minus over, when you factor this, you get x times x minus 3 times x plus 2. So that is our factored denominator. Now, this is where it starts to get weird. We're going to set this equal to the sum of some fractions, each one with one of the factors of the denominator. We're just going to put random variables in place. Traditionally, it's capital from a all the way to however many you have. So we're going to say a over x as our first one, plus b over x minus 3 is our next one, plus c over x plus 2. Now, the reason we do this is because, remember, the first thing we have here is an integral. That's the whole thing that we're trying to solve. These, if we knew what these were, would be a lot easier to solve because we can just split this up, and those denominators are a lot easier to work with. And this equation is true, we just don't know the values of what makes it true. So let's solve to get these constants, and to do that, we're gonna need a common denominator, and obviously that would be this. So what we're gonna do is multiply each of these missing components by whatever's missing to get that. So we already have our x, so we're gonna multiply x minus 3 and x plus 2 over the entire denominator, plus b times, we've already got our x minus 3, so we're gonna multiply x and x plus 2 over the common denominator, plus c times the other two over this, and there we've got that. And now our common denominator just cancels out. Usually I skip that step, I'm just showing you I go straight to our numerator equals these, just because it's a lot less stuff to write. So pretend this bottom part just doesn't exist, that was just a visual aid. So now what we're going to want to do is distribute all of these out so that we end up with that mess. So you can see all this is just these distributed out. And now that we've got that, we're going to rearrange this and combine our like terms with x's. So what I like to do here is say we're going to start with our highest exponent, so that's squared. So we've got an ax squared, a bx squared, and a cx squared. So I'm going to say a plus b plus c, all of that times x squared. And then I'm going to cross these out so that I know that they're done. Then we move on to exponent 1, which is just x. So plus negative a plus 2b minus 3c times x. And then exponent 0, which is just 1. So that's our constants, which is just minus 5a. So this is all now rearranged in here. And now you can see that this matches the form of this thing. So by comparing these, we know that a plus b plus c for the coefficient on x squared has to equal 4 because that's the coefficient here, so we say equals 4. So I think part of that clip cut off on my top down because the memory ran out, but ultimately what we know from this is since this matches the form here, we know a plus b plus c has to equal 4 because these coefficients match. We also know negative a plus 2b minus 3c has to equal negative 4 because that's what these coefficients are. And we know negative 5a has to equal 6. Now if one term is missing here, like if this negative 4x wasn't here, if it was just 4x squared plus 6, we would just say that that coefficient is 0. We're adding 0x. And so we would set this equal to 0. That's a step that I needed to have explained to me. But anyway, this is what we've got right now. So now we've got 3 variables and 3 equations. We can just solve this as a system of equations. You know, I'm sorry, this is supposed to be 6a. Just noticed that. So I'm just gonna casually, yeah, there we go. Nothing happened. So I'm going to start with the most obvious here. If negative 6a equals 6, then obviously a equals negative 1. So that's our first constant. So then we're left with b plus c equals, I'm going to change -1 for a and then add that over here. So that's 5. And then I'm just gonna solve this for one or the other. Let's just say b. So b equals 5 minus c. So then over here, we can plug in both of these. So we say -a is +1 plus 2 times, we said b is gonna be 5 minus c minus 3c equals -4. And now we can solve for c to get c equals 6. No, what did I do wrong? Ugh, fine, I'll solve it properly. C equals 3, so that's that constant, and then we can just plug this into here, which we had before, so 5 minus 3 is b equals 2. And there we go, we've got our 3 constants. Now, what was the point of doing all that? Well, if you look back at our original equation here, where we have our integral, and we said this fraction equals this sum of simpler fractions, we know what these constants are now. So let's plug in those constants. So this is what that equation was, except with the constants plugged in. Slap an integral back on this, because that was the original problem. And whoa! I don't know about you, but that looks a heck of a lot friendlier to me, because now we can just split this up into 3 super easy integrals. Hold up. How is that even? What? That looks nothing like the original problem. You're darn right, but that's the point, because they're still equal. Because look at this, if I were to add these fractions back up by getting that common denominator, multiplying these out, multiplying these numbers by that to get the common denominator, then we just get the same numerator and the same denominator. It's the same. That's the fraction that we had in the first place. So all this is just the steps you take to decompose this fraction and make it so much simpler. Hence, partial fraction decomposition. Now I'm gonna gloss over the actual integration because this is ridiculously easy. We did stuff like this in the first video. So bada bang, bada boom, plus c, and we are done. That is the answer to this horrendously ugly integral, which, if you do the right steps, isn't so ugly after all. It's just the algebra that's ugly. Wait, it's all algebra? Always has been. Now, if the degree of the numerator is greater than the degree of the denominator, then what you have to do is long division of polynomials. So what that will do is give you a sum of some super easy integrals, and then the remainder of your quotient is what you do partial fractions on, because that will have a decreased power in the numerator such that it will be less than the denominator. Unless it's not, and then you just do long division on that over and over again until you get it. Usually it's only once. Anyway, moving on to case 2, which is repeated linear factors. So, if we have something like that, then the denominator would factor out to that. Or, in other words, that is all equal. So what we do for that, since this is actually 3 terms instead of just 2 like it might look like with the exponent, we're gonna split it up into 3 fractions. So that would be a over x minus 1 plus b over x plus 1. Now, this is where it gets weird. Plus c over x plus 1 squared. What? If you're gonna put the square, why not just make it 2 fractions with the, and why do you need this if you're just gonna do that? That's not even, that doesn't make sense. You know what? You're right. It doesn't. This is Calc 2 where nothing makes sense. But the way this works, if that was like a cubed, you would say b over x plus 1 plus c over x plus 1 squared plus d over x plus 1 cubed. You just keep going, incrementing the exponent by 1 until you reach whatever that number is, if that makes any sense at all. But then, when we're multiplying this out, we still want that common denominator. So we would say our numerator equals this times whatever it takes to get a common denominator, so that'd be a times just x plus 1 squared. We don't need to multiply by both of these. So just x plus 1 squared plus b over, we're missing an x minus 1, and a single x plus 1 to get that common denominator, and then plus c times all we're missing is an x minus 1. So we don't need to multiply that because that's all it takes to get this to your common denominator. Why we need this in the first place, that's what I was confused on before. I still don't know, but whatever, that's how it works. So now, we just do exactly what we did before on this. I'm gonna gloss over it. You can just trust me when I say that the constants would come out to a equals 3, b equals -1, and c equals -3. I did the math in my notes on that beforehand. So now we're gonna plug those into our original equation. So there's our substituted values with our integral, and now this equals that. And of course, when we split this up, these first two are super easy. It's just that simple natural log thing. But be careful with this last one, because what you can do is turn that exponent that's in the denominator into a negative that's in the numerator to get that whole thing out. So we end up with that equals this. See, I just pulled out the -3 as our constant, and then 1 over x plus 1 squared is x plus 1 to the -2. That's our properties of exponents. And now you can just do our substitution for u equals x plus 1, and ultimately we end up with -3 over x plus 1. So we just tack that on to the end here, plus c, and there's our answer. And that is how you do repeating linear factors. Now, quadratic factors are going to be a little bit different. So let's say we've got this mess. The denominator, if you were to factor that out, would be that whole thing. And as you can see, there's an x squared inside there, so this is a quadratic factor. We can't factor it any further into linear factors. It's irreducible, so what do we do with that? We're still gonna have two fractions, because this is two factors. So the first one is really simple, just linear like we did. That's this factor. And then for the second one, so that's just the same as what we did for our linear factors. But what this numerator actually is that's a polynomial with a degree 1 less than the corresponding factor. So for linear factors, since the degree of this factor is 1 less than that is 0, and so that's just a constant. So we just write a. But for quadratics, 1 less than that is a linear factor. So as our numerator, we're gonna write bx plus c. You can see we have a term with x in here because that is a degree 1 less than 2 is 1, so we need x to the first power. And then that is over x squared plus 4. So that's our equation, this equals that. And we need to find those constants. So we just need to figure out how to find that common denominator, cancel out our stuff. So we end up with our numerator, x squared minus x minus 21, equals a times x squared plus 4, plus bx plus c, that whole term, times 2x minus 1, which is this. So now we just distribute that and combine like terms like we did before. I'm gonna gloss over that. We get this mess, at which point we can start figuring out our coefficients. So like we know a plus 2b has to equal 1 is the coefficient there. We know negative b plus 2c has to equal -1. And we know 4a minus c has to equal -21. 3 equations, 3 variables, let's go. Once again, I'm gonna skip over actually solving it because we know how to do that from here. We end up with a equals -5, b equals 3, and c equals 1. So those are our constants. We can plug those in to this equation. So we get this madness. Slap an integral on that boy and let's get it and solve. So our first one is super easy. It's just that, same as our other linear factors. This one is a bit trickier though. At first glance, it might not even look that much better than what we had in the first place, because we got, like, do we solve this with partial fractions again? I mean, we can't even factor that, that's what we had in the first place. But what we can do is split this up into 2 fractions with that denominator, because since the numerator is a sum, we can say that is the same as 3x over x squared plus 4 plus 1 over x squared plus 4. And now we can solve these individually. So the first one is super easy. We just do our substitution and get yet another natural log. But this last one is going to be tricky again because we have an x squared, but that's it. So if we sub that in, we're not going to be able to cancel anything. Now there's a couple of ways to handle this, but for the sake of time, I'm just going to do it the quick way and say, hey, that looks almost like the derivative of tan inverse. So how can we make that match? Well, we can just factor out a 4 in the denominator like that. So now we have 1/2 x all squared, so that'd be 1/4 x squared, which multiplied by 4 is just x squared, which is what we had, plus 4 times 1 is 4. That's an accurate rewrite, you know what I'm trying to say. So now we can, this is an integral, we can pull out the 1/4 and then do our u sub on that 1/2 x, and ultimately we would get 1/2 tan inverse of x over 2. Because remember, the integral of 1 over x squared plus 1 is just tan inverse x. That's in our table. So by substituting, we can make that in our table. This is the result we get. Tack both of these onto our final answer, if it'll fit. Close enough, plus c. There we go. Whew! Oh, we're done. So that's how you do quadratic factors. Now, there is one more case, and that is repeating quadratic factors. Oh boy. Alright, so we've got this thing. Holy moly, that's a thing. Alright, where do we start? Well, before anything, let's make sure the degree of our numerator is lower than that of our denominator, which at first glance it looks like it's not, because the highest number here is 3 and the highest number here is 2. But when you multiply this out, that's actually a 2 times 2, which is 4, so we're good there. So that means we do not have to go through hell trying to long divide this. So double checking that this is indeed fully factored in the denominator, let's split this up into our fractions, combining the techniques that we used for repeated linear and single quadratic to get the technique for repeated quadratics. So that'd be a over x plus bx plus c over x squared plus 1. That's our first quadratic, and then plus dx plus e over the second version, which is going to be x squared plus 1 squared. So that's just combining the techniques here. Now, there's really nothing new here, so I'm just going to go common denominator. Alright, that's a mess. Now what? Holy crap. Okay, let's combine like terms quick before this rips a hole in the space-time continuum. Okay, cool. So that's still really ugly, but if you look at it, it is a bit nicer to work with because now we can start matching things. Now, as you can see, we have a plus b for our coefficient to x to the 4th, but we don't have an x to the 4th here. But what if we did and it's just invisible? Calc 2 where nothing makes sense! There actually is an x to the 4th there, it's just being multiplied by 0. So we say a plus b equals 0 for that coefficient. If we go all the way down doing the rest of them, we would get 5 equations for our 5 unknowns. I'm gonna save you the mind-numbingly long time it would take to do that and just tell you that a equals 2, b equals -2, c equals 1, d equals -4, and e equals 2. So if we were to solve this whole thing, that's what we would get. So we've got all our constants for our original equation. You know what that means, plug and freaking chug! Alright, so there we go, there's our new integral. First one's easy, just 2 natural log x. Second one, we're gonna do what we did before, split it up, pull a u sub, whip out that tan inverse, which will give us that boy. Now the last one is even harder. Let's split it up. I'm gonna start the first half with a u sub, saying u equals x squared plus 1 inside those parentheses. And that's actually pretty easy. It's just what we did before with the last one. So we end up with 2 over x squared plus 1. And there's our first half of this one. For the second one, that looks almost like a trig sub, so let's just pretend it is. Slap a triangle on it. So x squared plus 1 is gonna be, or root x squared plus 1 is gonna be our hypotenuse here, because it's in the form x squared plus n squared. So that means x and 1 are sides. Theta here will get us tan theta equals x over 1 is just x. Dx is secant squared, theta d theta. So if we plug that substitution in here, we would get, I'm gonna pull out that 2, 1 over secant squared theta plus 1 squared dx. Or wait, no, hold up. Secant squared theta d theta. So there's our trig sub. And first of all, this denominator can become secant squared theta squared, or just secant to the 4th theta. And then, since this secant squared is being multiplied by that, we just subtract it out and we get 1 over secant squared. And then this, by using the definition of what a secant is, that's 1 over cosine, that can just be transformed into cosine squared theta. And from there, just sprinkle a little half angle formula on this boy, split it up, a little something something in between, and we end up with theta plus sine theta cosine theta. So now we need to solve for what theta actually is here, which, using this, we can just say it's the inverse tangent of x. So we do our switcheroony back to x, and that is our second half of the second half of our big integral. So stringing this all together, we get that monstrosity. And we can clean this up a little bit. You can see our 2 tan inverses cancel. These can be combined into 1 fraction. So ultimately, plus c, that is our answer. Oh gosh, I need a break, dude. That was... Alright, so that was partial fraction decomposition. We're gonna continue the theme of getting funky up in this boy and deal with something called improper integrals. Now this concept is way simpler than it sounds. It's just doing definite integrals where infinity is involved somewhere in your integral. I promise it's simpler than it sounds. Integral of 1 over x from 1 to infinity. What do we do with... Okay, so this is something we don't know how to do, this little infinity here. So, we're just gonna do what we always do in Calc 2 when we discover something we don't know how to do. Just get rid of it. Let's call this b, so integral of 1 to x from 1 to b. So now this is solvable. We would just do the indefinite integral to get natural log of absolute value of x, and then take that from 1 to b, which would be natural log of b minus natural log of 1. Natural log of 1 is 0, so that's just 0. Now let's put infinity back in there, but instead of actual infinity, we're just going to solve this for b as b approaches infinity. So we're going to take the limit, whoa, that's a concept we haven't used in a while, as b goes to infinity of natural log b. So this, since natural log just goes up infinitely, that would equal infinity. And we say this integral is divergent, which makes sense. I mean, you're adding an infinite amount of space, right? But let's say we have integral from 1 to infinity of 1 over x squared dx. So we're going to change that to 1 to b, and then that is just x to the negative 2. So following our power rules, we get negative 1, x to the negative 1, which is just negative 1 over x. Take that from 1 to b, and we get this equation. And so we're going to take the limit as b goes to infinity. So this is still correct, right? This still matches. But now, as b goes to infinity, since it's in the denominator of this fraction, that means this fraction goes to 0, because we're dividing by bigger and bigger numbers, which means that fraction is just going to 0. So we end up with 0 plus 1 equals 1. So wait, you're telling me that the area of this infinite space that goes on forever and is never actually 0 isn't infinity? It's 1? Yeah, I didn't get this at all. Actually, until I wrote this script to give you an example. Think of, I think it's Zeno's paradox, where he says motion is impossible because in order to get somewhere, you have to get halfway there. In order to get there, you need to get halfway there, all the way on until forever. So you can't ever really move anywhere. But obviously this is false because, I mean, whoa, my hand moved. So let's say I want to measure the distance from here to here, this line. I want to measure that distance. So the way I'm going to do this, because I hate myself apparently, is I'm going to measure first half the distance. So I'm going to measure out this distance and then add half the remaining distance, like that, and then add half that over and over again and never really actually get there. So you can see here, we're going to be adding up an infinite number of measurements, and each of those measurements has a quantifiable value. Like it never reaches, we're never adding 0. So logically, if we keep adding numbers here, you'd think the sum would just keep getting bigger and bigger and bigger until it reaches infinity. But visually, you can see here that it does go from here to here. There is a start and end, and this is a quantifiable length. So the concept that makes this work, even though you're adding an infinite number of values, the values themselves are getting infinitesimally smaller. It's the inverse of infinity. So this behavior kind of counteracts each other, and you can get one actual quantifiable number. I don't know, this just blew my mind. I didn't understand until I thought of that, but with that in mind, there's another scenario where that actually doesn't work, because what if your graph looks like this? That's kind of what we had here. That's like roughly-ish the graph of natural log x. So these values keep getting bigger and bigger, and so we're adding more and more area, so this does exactly what you'd expect and goes on to infinity, as we proved in the first place. So that's what we call a divergent integral. Whereas this one, since it approaches a number, is called convergent. Now, let's take a look at another kind of divergent integral. Like, let's take integral from 0 to infinity of sine x. Now, without even solving this, you can tell there's going to be a problem, because as sine goes to infinity, it just keeps oscillating between -1 and 1, -1 and 1 over and over again, and it never approaches one number. So the limit of this thing, as our upper bound goes to infinity, does not exist, or dne. Now you might think, if we're taking the area under the curve, that's what an integral is, if we're taking the area, and this never approaches a number, we just keep adding area to this, more and more area, it makes sense that it's going to diverge, because it just keeps blowing up to infinity, right? Wrong! Kind of. It is divergent, but the area isn't infinite, because it's only above the x-axis half the time. So what we're doing is, this is negative area here, that we are continually adding and subtracting area from this. So the area itself is also oscillating between -1 and 1. That's why the integral of sine x is negative cosine x. But since it never approaches one number, it's going back and forth, we still call it divergent. Because as it goes to infinity, that number is undefined. So those are the three cases with improper integrals. One, it goes to an actual number, it converges, and we can find that number. 2, it goes to plus or minus infinity, in which case it's divergent. Or 3, the limit doesn't exist, in which case it's also divergent. Now let's talk a bit more about that third case, because oscillation with sine and stuff isn't the only way to get that. For instance, let's take the integral from -infinity to 0 of x e to the x dx. Now I'm not going to bother showing you how to integrate this, we just do parts. And get limit as a approaches -infinity, because that's our lower bound this time, so we're going to do a instead of b. Doesn't really matter, it's just convention. So the limit as a approaches -infinity of -1 minus a e to the a plus e to the a. That's what this definite integral would be. So look at this, as a goes to -infinity, e to the a goes to 0, because that'd just be 1 over e to the infinity. But then over here, we have this as a coefficient as well, meaning we have -infinity times 0. So, what happens when an unstoppable force meets an immovable object? Well, that is what we call indeterminate form. So what we need to do then is rewrite this so that it's either infinity over infinity or 0 over 0. And then we can use L'Hopital's rule, which was taught in, I think, pre-calc, maybe calc 1. It's a topic that I'm not going to go over because we should already know that in theory. So first let's get rid of the easy stuff. -1 is just -1. E to the a goes to 0. So we're left with minus limit as a goes to -infinity of a e to the a. And that can be rewritten as limit as a goes to -infinity of a over e to the -a. Because by making this a negative, it's just 1 over, which equals that. But by having it in this form, that is now an infinity over infinity thing. Because as a goes to -infinity, negative infinity is positive infinity, meaning e is blowing up, as well as a is blowing up to -infinity. So that is a thing. So now we can use L'Hopital's with this. Just take the limit a to -infinity, take the derivative of the top and bottom. So that leaves us with 1 over negative e to the -a. And hey, that's more doable. Now as a goes to -infinity, we can clearly tell that e is going to blow up to infinity, meaning since it's in the denominator, this whole fraction goes to 0. So then we just add that to the 0 that we had here, minus the 1, and we're left with -1 as our answer for this improper form integral. So we just add that to the 0 and the -1 that we had before, and we're left with -1 plus c. No, this is a definite integral. We don't need plus c. It is improper, but it's still definite. So -1 is our answer here. Also, by the way, if you have something like integral of negative infinity to infinity of f of x, I'm just gonna call whatever formula you have in here f of x, you can split it up into negative infinity to c f of x plus from c to infinity f of x, where c is any number you like. Usually 0 makes things easier, and that just makes things all around better to deal with, because who wants to go from negative infinity to infinity? So that's basically all it is. If infinity is somewhere within your function, it's the same idea. Like, let's say we have integral of 1 over root x dx from 0 to 9. That's not going to work for x equals 0, because 1 over 0 is infinity. So we simply say limit, yes, I like my m with extra humps, please. So we just say limit as c approaches 0 from the right, that's important, I don't know why, but it's important, of c to 9, 1 over root x. And then we just solve from there. That's easy peasy. If it was some number in the middle of our bounds here, like if we had taken this from negative 2 to 9, 0 would be in there, but we would just split it up like we did here and just say like negative 2 to c and then plus c to 9. Take our limits, add them up, you get the idea, right? So that's pretty much it for improper integrals. Now, I'm also gonna I already used that, so I'm also gonna throw this in there. This was week 4, it's just kind of its own thing, it's super quick. We're gonna go over surface area of revolution. That is, if you have a graph here like that, and you wanna take from here to here, and you revolve this around an axis, in this case the x-axis, you end up with something like that. Now, taking the volume of this, I think we already learned, and that's super easy. You just take the integral and multiply it by pi r squared or something like that. But to find the surface area of the outside, that's a little different. Now, there's pretty much just one formula for this that you're gonna stick to, and there are way more complicated ways to explain this, because the way it makes sense intuitively isn't actually the way it works, but it doesn't matter. It's a formula and it works intuitively by looking at it to me, and so let me show you why. So our formula is surface area equals integral from a to b, where this is a and this is b, of 2 pi times f of x, where this is f of x, our function there, times the square root of 1 plus f prime of x squared dx. Boom. There's our formula. That's basically the entire section. We spent a week on that, but let me explain real quick. So the goal here is we have some function, f of x, and we're revolving it around the x-axis. Now, we're going to find the surface area of this outside shell, and all we need to do for that is split this into an infinite number of circles, just like we do with volume, but then multiply the circumference of each one by the length of that curve from one to the next, which we find here by using the Pythagorean theorem and the length of the curve. So like if we have one section here, that's horrible. One section here, one section here, one section here, something like that. You can break this up into lines. Remember, when we're doing our integral, these spaces are infinitesimally small. But for visualization, we're saying we want to find this length from one section to the next. And that is going to be our teeny tiny infinite Pythagorean theorem, which states that you take the difference here and the difference there, and that'll give you the distance from the edge of one section to the edge of the next. And so for the x value, that's just 1, we use our unit value. And for the y, that is going to be the slope of your function at that point, or the derivative of f of x. A squared plus b squared, take the square root of that, that's going to get you c, which is that distance. And then you multiply that by the radius of the function at that point, which is f of x. That's going to be your r for 2 pi r, because the circumference of a circle is 2 pi r. So that's just the circumference times the arc length. It's just a combination of circumference times arc length. Now, obviously there's a lot of stuff missing in there, but that's the explanation that works for me. If you want the actual explanation, there are a number of videos out there that you can watch, but this is good enough for me. So this is for revolving a function around the x-axis. If you're revolving it around the y-axis, you literally just replace all the x's with y's, which of course means you need to solve your original function for x. But yeah, that's pretty much it. That concludes week 4, and that also concludes this video. So thank you so much for watching. If you enjoy this stuff, please leave a like down below. If you really loved it, maybe that even earns your subscription, and that would be much appreciated. It really helps me out a lot. I know I haven't been great in doing actual content lately, but I promise I do have so many things in the works, and I'm planning to get some stuff out real soon. By the time this video comes out, I will have officially reached my first $100 on Patreon, so thank you to the few of you that have gotten that started. I sincerely appreciate it, and that money will be spent toward, I don't know, something for projects, film equipment, definitely something good, and definitely something soon. Because I have been holding off on a lot of things until I had a decent amount to spend on it. If you would like to jump on that bandwagon, head over to patreon.com/fluffballthewizard. Just sign up for whatever you can afford, every dollar counts, and you will get access to some exclusive benefits. That's all for now, thank you again for watching, and until next time, make something, sing something, still virtually hug someone, and I will catch you in the next video. Oh! That's a little more aggressive than I intended. Good work, frick me. So basically we just need to replace secant, tangent, and what did I just say? I don't even know.